Chapter 4 is all about triangles. Section 4.1 is called the triangle sum theorem. But before we can get into this first theorem, let's first identify and define what a triangle truly is. A triangle is a polygon. So notice that the word polygon is within the definition of what a triangle is. The definition of a polygon is a closed plane figure, meaning that all of the sides connect and it can fit on a flat surface. So a triangle is a polygon with 3 sides. I bet you're thinking, I already knew that. Of course you did. But let's talk about how you talk about triangles and how you name them. So a triangle is named by its vertices. Remember, vertices are like the points where all the sides come together. So in this diagram, I gave you a triangle with vertices A, B, and C. The symbol for triangle is a triangle itself. So I could either call this triangle with the word triangle ABC, or I can use this symbol, which, like I said, is an actual just triangle. So you could say triangle ABC. Notice how I put it in alphabetical order. It is not a big deal to write them in not alphabetical order. You could have said CBA, you could have said BAC, but typically you just start with one of the vertices and go in one order and go all the way around when you're naming a polygon. So triangle ABC. If I started with the C and I could have gone this way, so CBA. But always start with a vertex and go in the same direction and name them in that order as they come. You can classify a triangle by its side lengths or by its angles. It is called a scalene triangle if no sides are congruent. If all 3 sides are different lengths, it is scalene. If 2 of the sides are congruent, it is called isosceles. ISOSCELES. I would say this is probably one of the most common misspelled words in math. Isosceles triangle, at least 2 congruent sides. So notice it says at least. Since there's 3 sides, if 2 of them are congruent, it is isosceles. If the third side is also congruent, you can also classify it still as isosceles. So at least means 2 or more. So if all 3 sides are congruent, you can still classify it as an isosceles triangle. The third way to classify a triangle by its sides is an equilateral triangle. So we've learned this word equilateral before. That means all equal sides. So an equilateral triangle is when all 3 sides are congruent. But remember, that also can fall under isosceles triangle since at least 2 of the sides are congruent. Let's move on to how to classify a triangle by angles. If all 3 angles are acute, so less than 90, it is an acute triangle. If one of the angles is 90 degrees, it is a right triangle. There can only be one right angle in a right triangle. There can never be more than one. An obtuse triangle is when one angle is obtuse, so greater than 90 degrees. And again, you can only have one obtuse angle. You cannot have 2 obtuse angles in a triangle. And an equiangular triangle is when all 3 angles are congruent. And again, we've seen this word equiangular before, just like we saw equilateral when we talked about polygons having all congruent angles. So those are the 7 ways of classifying triangles, either by its side lengths or its angles. Let's look at an example. We have number 1. Part A, classify triangle ABC by its sides and by its angles. So if I'm supposed to classify it by its sides, I will need to find the length of all 3 sides. Notice how all 3 sides are diagonal lines. Therefore, it's not going to be as simple as just counting units if the lines were completely horizontal or completely vertical. So I'm going to have to use the distance formula. So let me remind you what the distance formula is. It's the big square root formula. So it's the square root of x2 minus x1 squared plus y2 minus y1 squared. So again, I'm going to have to find the length of all 3 sides, the length of AB, BC, and AC. In order to do that, I need to find all the ordered pairs. So let's get to that. So for point A, they're going to the left 1, 2, 3, 4, 5 units to the left and up 1, 2, 3, 4. So the ordered pair for point A is -5, 4. For B, they're going to the right 1, 2, and up 1, 2, 3, 4, 5, 6. So it would be 2, 6. And while we're at it, let's do C. they're going to the right 1, 2, 3, 4, and down 1. So the ordered pair for C would be 4, comma, -1. So again, we're going to have to find the lengths between all three sides. So let's start with AB. I have the square root of, subtract the x's. So let's start with that 2 minus -5 squared plus 6 minus 4 squared. 2 minus -5 would be plus +5, which would give me 7, and 7 squared is 49. So I would have square root of 49 plus 6 minus 4 is 2, and 2 squared is 4. So I have 49 plus 4, which, to simplify, gives me the square root of 53. That doesn't really tell me much unless I do a decimal approximation, so I'll do a little squiggly and do that in my calculator, which gives me about 7.3 units. Let's now find the distance between B and C. So again, I'm going to draw my nice big square root, subtract the x's. Let's start with that 4 minus 2 squared plus 6 minus -1 squared. And 4 minus 2 is 2. 2 squared is 4. 6 minus -1 would be plus +1. So 7 squared is 49. And so once again, I get the square root of 53, which is about 7.3. So far we know that this is at least an isosceles triangle, since we have two sides that are congruent. Let's finally find the distance between A and C. So again, let's give ourselves a nice big square root. Let's start with the 4 minus -5 squared plus -1 minus 4 squared. So 4 minus -5, I'm kind of run out of room, so I'm going to put it down here. 4 minus -5 is 9. 9 squared is 81. -1 minus 4 is -5, and -5 squared is 25. So if I add those together, I get the square root of 106. To find that in my calculator, to get a decimal approximation, I get about 10.3. So again, I see that I have two sides that are equal, so I would classify this as an isosceles triangle. So somewhere I'm going to write in here so you can actually see it, since I used up so much of my space, that this is an isosceles triangle. I put that in red so you can see it. And part B asks, how would you show that triangle ABC is a right triangle using the lengths of the sides? So if you remember from last chapter, we know that two sides are perpendicular if their slopes are opposite reciprocals. So just by looking at this diagram, I see that perhaps line AB is perpendicular to line BC. And I'd be able to prove that again by finding the slope between A and B, finding the slope between B and C, and checking to see if they are opposite reciprocals of each other. So let's do just that. So the slope between A and B, so segment AB, would be, I'm counting up 1, 2, and over 1, 2, 3, 4, 5, 6, 7. So I went up 2 and over 7. If the slope of BC is -7/2, I know the two sides are perpendicular, and therefore this would be a right triangle. So let's find that. Start here at B. I'm going to count down 1, 2, 3, 4, 5, 6, 7, and over 2. So look at that. The slope of segment BC was down 7 and to the right 2, and therefore I can see that these two sides are opposite reciprocal when it comes to their slopes. So I have therefore proven that triangle ABC is a right triangle. Before we get into the theorems associated with this section, we first have to identify and define what interior and exterior angles are. Notice in our diagrams that the sides of the triangles are extended, and this can be done in other kinds of polygons as well. But again, when the sides of a polygon are extended, notice that other angles are formed. So looking at the diagrams, you can see that the sides of the triangles are extended, and we now have 4 angles here that were formed, and 4 angles here, and 4 angles here. Each one of those angles are called something special. Let's first identify interior angles. Interior angles are the original angles in the triangle. So again, in the diagram, you can see they are marked here in red. Those are the interior angles. Next, you can see we have exterior angles. These are the blue ones in the diagram at the right. Exterior angles form linear pairs with the interior angles. So if you look at our diagram at the right, here is an interior angle, and the blue angle right here would be a linear pair with that interior angle. The same goes for this side, this blue angle here. It is forming a linear pair with this interior angle. Notice that each interior angle has two exterior angles that are adjacent to them. Therefore, each interior angle has two exterior angles that it is forming linear pairs with. And again, we need to be able to identify what interior angles and exterior angles are in order to state the two theorems that are associated with this section, which will be following this slide. So again, here's the two theorems. Actually, it's two theorems and a corollary, which we've talked about corollaries are before, but we'll revisit what they are in this slide. So the first theorem is theorem 4.1, and it is called the triangle sum theorem. It states the sum of the measures of the interior angles of a triangle is 180 degrees. So basically it's stating that if I take, and this is true for any triangle, if I take the sum of the interior angles of a triangle, they would all equal 180 degrees. Next is theorem 4.2, the exterior angle theorem. It states the measure of an exterior angle of a triangle is equal to the sum of the measures of the two non-adjacent interior angles. There's a lot of words in that theorem, so let's break it down. If I take the sum of these two angles here, I would get the measure of this exterior angle right here. So basically, if you're finding the measure of an exterior angle, you go to the two angles that are opposite them, the furthest away from the exterior angle. You add those two together and you will get the measure of that exterior angle. So again, the measure of this exterior angle is equal to the sum, which means I add, of the two angles that are furthest away from that exterior angle. So let me give you an example. If I took the measure of angle A and added to the measure of angle B, I would get the measure of angle 1 here, the exterior angle. So let's say that the measure of angle A is 50 degrees and the measure of angle B is 70 degrees. I would take 50 plus 70, which is 120, and that would give me the measure of angle 1. Next, we have a corollary. A corollary to a theorem is a statement that can be proved easily using the theorem. To me, a corollary is something that is a direct result because of a previous theorem. Because I know that something is true, I know this new thing as a direct result from it. So this is a corollary to the triangle sum theorem. Now remember, the triangle sum theorem states that the sum of the interior angles of a triangle are equal to 180 degrees. So this is the corollary to that. It says the acute angles of a right triangle are complementary. So this is true because I know that the angles in a triangle are equal to 180 degrees. So I have one 90-degree angle if I have a right triangle. So if this is 90 degrees, that only leaves 90 other degrees for A and B to add up to. So therefore, neither A nor B could equal more than 90 degrees. So A plus B would always have to equal 90 degrees in a right triangle. Example number 2, find the measure of angle 1. So you see here in the diagram that we have an exterior angle right here, and we have two angles that are far away from this exterior angle. We learned in the last slide that the measure of an exterior angle is equal to the sum of the two angles that are furthest from it. So I could set up the equation to look like this. 5x minus 10 equals 3x plus 40. So first I'm going to solve for x and then be able to plug it back in to find the measure of this exterior angle right here. So the first thing I would do is subtract the 3x from both sides. 5x minus 3x is 2x. Minus 10 equals 40. So then I would add 10 to both sides. 2x equals 50. Divide both sides by 2. and x equals 25. But notice I was not asked just to find x. I was asked to find the measure of angle 1. So now that I know that x is equal to 25, I can substitute it back in up here to find the measure of angle 1. So I can find the measure of that exterior angle by taking the 5x minus 10 and substituting 25 in for x. So I would have 5 times 25 minus 10. 5 times 25 is 125, minus 10 is 115. However, this angle is 115 right here. I'm asked to find the measure of angle 1. Notice that angle 1 and this angle 5x minus 10, which we now know is 115 degrees, forms a linear pair. Therefore, I can find the measure of angle 1 by taking 180, since a straight line is 180 degrees, minus 115. So again, the measure of angle 1 would be 180 degrees minus 115 degrees. Therefore, to answer the question, the measure of angle 1 is equal to 65 degrees. And our last example, number 3, find the measures of the acute angles of the right triangle in the diagram shown. We can use the corollary in this section in order to solve this. Since I have a right triangle, it's marked here, a right angle, so this is a right triangle. I know that the two other angles in the triangle have to be complementary because there's 180 degrees total inside the triangle, and if one of them is 90, that only leaves 90 degrees for these two angles to add up to. So I'm going to take 2x plus x minus 6 and set it equal to 90. So first I will combine like terms. 2x plus x is 3x. Add 6 to both sides. So I end up with 3x equals 96. Divide both sides by 3 and I end up with x equals 32. But remember, this does not say just to find x. It says find the measures of the acute angle. So now that I know that x is 32, I'm going to substitute it back in to both of these to solve for the two angles. So one of them would be 2 times 32, which is 64, so it'd be 64 degrees. And our last one is x minus 6, so I would take 32 minus 6 to get 26 degrees. Another way I could have found it was by taking 90 minus the 64, which I still would have gotten 26, since I know that these two angles had to be complementary, which means they had to add up to 90 degrees. So again, my two answers were 64 degrees and 26 degrees. And that's it for this section. Make sure you jot down anything in your notes that you don't understand that we can cover before we move on to the book assignment for this section, and we'll see you then.